Okay, good morning, everybody. So I hope you're all holding up fine with the typhoon. And so I think we can get started as soon as I can work out the screen sharing. All right. Okay, so I'm sharing my screen. Hopefully you can all see that. So I thought actually, we haven't really finished chapter 3 yet, but I just want to go through some of the things in chapter 3 with the vector product or the cross product with the whiteboard, and it's pretty awkward on Zoom. So I thought we might just come back to that and start on chapter 4 today. We can talk about that stuff maybe in the next lecture on Thursday. Okay, so let's get on to chapter 4. So basically what this chapter is doing is to kind of combine the ideas of chapters 2 and 3. So in chapter 2, we did motion in one dimension. And then chapter 3, we did vectors. So this is combining those two ideas and looking at motion in 2 and 3 dimensions. We're going to do things like projectile motion and things like that. Okay. So, first, a few definitions. So if we want to define a position in, this is 3 dimensions actually, but equally in 2 dimensions, we can have a 2-dimensional vector instead here. So we can basically define the position of an object with reference to some coordinate system, which we set up. So we can basically set the origin to be anywhere that we like. And then with respect to the origin and the coordinate axes, we can define a particular position of an object. So in this diagram on the left, we've got something which is some direction along -3 meters along the x-axis, 2 meters along the y-axis, and 5 meters sort of vertical along the, vertical is y here. So 5 meters in the z direction. Okay, and so we can write this with the unit vector notation as we've learned. And as I've said, this is the basically the same as the coordinate kind of representation. So I kind of consider them to be more or less the same kind of thing. So if we've got x, y, z coordinates, then it'd be x times unit vector I, y plus y times unit vector j, and z times unit vector k. Okay, so that's how we define positions. And I think we've actually already encountered this in the previous chapter, but we can also define displacements, and displacements are basically just a change in the position of some particle. So in this, on the diagram on the right here, if we've got some particle which is moving along this trajectory, this curved trajectory here, the say position at some particular time 1 and particular time 2, those would be say R1 and R2 vectors, and each of those would be for example, so 2 vectors that we define like on the left here. So xi, yi, zi, maybe that's the R1, and xf, z, yf, zf is R2. And then the displacement is just a change in the position of these 2. So it's basically, again, the final position, which is the vector R2 in this example, and minus the initial position. So we just basically subtract the coordinates, and so in the coordinate representation, it's just the changes in the position of along the x, y, and z axis. Okay, so that's just the displacement. And just like we did with one-dimensional motion, we can define an average velocity. So this means that you look at basically the displacement divided by the time that it took to perform that movement. So the displacement here is the delta r vector, and that is divided by the time. So, for example, in this example here on the right here, if it goes from A to B, the displacement vector is the delta r, and if it takes some time t, delta t, in order to perform that movement, then the average velocity is basically defined according to this formula. This is again a path-independent object, so it doesn't matter if it happened to take any one of the paths that I've drawn here. So if it's the path in red, or the that's the direct path, or the gray one, or the pink one, they would all actually give the same average velocity. And again, we can write it in terms of coordinates like this. Okay, and then we can also define an instantaneous velocity. So this is, of course, the velocity at that particular time. So that particular instant in time. So if you take the limit of two displacement vectors being extremely close together. So imagine if you take this R1 and R2, and these are 2 points in time. Now, if you consider two time intervals which are extremely close together, so we're moving basically 1 and 2 very close together, right? Then if you look at what would happen to well, firstly, the direction of the displacement. So for this particular example here, the displacement vector from 1 to 2 is pointing along this blue line here. By the way, you can see my mouse? Can you? Can somebody just say whether you see my mouse moving?
Yes, we do.
Okay, great. Okay, right. So along here, 1 to 2, that is basically the direction of the displacement vector for this example. Now, if you move 2 closer and closer together to 1, then you'll see that actually gradually this displacement vector will move a little bit more towards like this tangent line, this like this pink line here. But when you get them extremely close together, then the direction will no longer really change, and so there is some kind of limiting value where the direction, the displacement will be exactly along this tangent line. So what you can kind of think of is that this average velocity, or like the small interval, is a kind of an approximation to the instantaneous velocity. And the closer and closer that you get these two displacements together, the more and more it will start to take the value or the actual vector corresponding to the instantaneous velocity. So of course, this is how you sort of define it in terms of an object, but actually the way you calculate it is much more simple. In a way, you simply actually just take the derivative of the displacement vector. So this is basically the definition of the derivative, and but computationally, in terms of how you actually would work it out, you would simply just look at the formulas for the displacement. So you first work out what your displacement vector is, and then you'd simply take the derivative of that. So basically the velocities for each of these components would be the time derivative of the x position, y position, and z position. As usual, we can always write it in terms of unit vectors or coordinate representations, basically always the same. Okay, so I think that's all I want to say here. I mean, maybe the other thing to notice is that the velocity, instantaneous velocity vector is completely, a different direction in terms, in comparison to the position vector. So the position vector might be pointing this way, and then the velocity vector will be pointing pretty much, a completely different direction to them. So even though you define the velocity vector from the position vector and you just take the time derivative, in terms of the direction, they might be actually quite different directions. Okay. Right. Okay, so let's have a look at this question. So the figure shows a circular path taken by a particle. So far it doesn't tell you if it's going clockwise or anti-clockwise. In fact, that's actually what you have to work out. If the instantaneous velocity of the particle is 2 meters per second along the x direction and -2 meters along the y direction, through which quadrant is the particle moving at the instant it is traveling, if it is traveling clockwise and counterclockwise? Oh, I see. So we're going to consider two situations of it's actually moving clockwise, like this way, and we're told that the velocity is 2 meters I, 2 meters per second I minus 2 meters per second J, and then we have to work out which quadrant it's in. So, well, you can either shout it out or you can just put it in the chat here. Nobody? Okay, cool. Got one answer. Great. Right. Maybe a couple of other people might like to answer. Or if it's confusing, then let me know what part you find confusing. Okay. All right. Okay. Okay, so we've got a couple of answers, and for part A, people are saying A, which is correct. So firstly, we've got to work out which way the direction velocity vector is, right? So, okay, so it's 2 meters per second I minus 2 meters per second J. That basically means it's 2 meters per second along the x direction, so it should be this way. And then -2J means down. So basically the velocity vector for that is pointing sort of diagonally down like this way. Now, if it's moving clockwise, well, we don't need to do any real calculations because we can just sort of imagine this particle moving, right? And so, for example, if it's moving clockwise, well, let's start here. So if it's moving clockwise at this position, instantaneously, it's actually going upwards, right? Because it's going this way. Now, if you imagine this as like a ball attached to a string, and then it's spinning around, and then you cut the string exactly when it hits this point, of course, it'll go flying this way, right? So that basically tells you what the instantaneous velocity is that point. Say here, if you cut the string here, it'll go flying to the right. So we're looking for the point in this motion where the velocity vector is pointing like this way. And if you just sort of follow the vector, so I'm going to sort of do the velocity vector as I move the mouse. So it'll be pointing like this way, and then here it will be pointing down. And in fact, that will be the only place that it will be this way, and then this comes back up. So this point here is really the only position where it's actually going to be pointing down. Okay, so yeah, so that's why it is A, and you would draw a vector that's pointing that way. Okay, for part B, Emily's already answered, but maybe some of you might like to also put your answers in. But this time we're looking at if the motion was the other way around. Now, it's no longer A, because if it's moving this way, now the velocity vector has to be pointing this way, right? So if we follow that motion, actually, B for B. Okay, so it looks like we've got a little bit of a split in how everybody's thinking. So all right, so let's follow this trajectory around. So here it's going counterclockwise, so the velocity vector is here. And follow it around, it's pointing this way. Over here for B, it's pointing this way, but actually we're looking for a vector that's actually pointing this way, right? So this is 2 in the X direction, and then -2 in the Y direction. So it needs to be looking like this. So okay, so let's keep on following it around. This point here is going to be straight down. At C, it's going to be pointing this way, which is the same as this. Yeah, so the answer here is C. And in this case, you would draw the velocity vector pointing up this way. Okay. Okay, I think everybody's converged upon C. Okay. Keep going. Right. So now let's talk about acceleration. So for acceleration, we can define it in a very similar way to one-dimensional motion, and basically that's done by looking again at the change in the velocity. So instead of displacement, which was change in position, we're going to look at change in velocity this time, and then we're going to divide by time. So the vector version, or the 2- or 3-dimensional version, formula looks exactly the same as it did for the other cases we've looked at. We simply just divide by this velocity change vector divided by the time. So okay, so this diagram, I didn't really have one that okay, let me see if I can draw something here. Okay, right, so so for example, in this particular path here, so the particle is moving along this trajectory here, and so at this point in time, I think you can sort of imagine that the movement is sort of, it's going up and then it's going down like this, right? So the particular velocity vector at this point, so let's call this like the, well, let's call this V1. The velocity vector V1 is like this. So for example, that's one particular point in time. And now let's look at another point in time, which is say around about here. Around here, the velocity vector, okay, I didn't draw that very well, but okay, something like this. Here's a position, and say the velocity vector is going to be this way. So this is going to be V2. So again, what we mean by taking the average acceleration is, again, we're looking at the change in these two vectors. So we subtract these two velocity vectors from each other, and there's definitely a change in the velocity here. We don't really know from this diagram like how long these vectors are. So I can't really say for sure that this is, this length, or longer, or and the reason why is because I don't know if from just by looking at this diagram whether it it sort of starts to speed up and then go down here, or if it's it's fast at the beginning and then at V2 it's actually almost grinding to a halt and it's very slow there. So the length of this vector, I'm just I have no information about that, but suppose it's something like the same length. Then what we're doing with the average acceleration in this case is to basically subtract these two vectors from each other. Now to do that, I'd have to I need to basically do the head to tail kind of rule for these vectors. So I'd have to take this vector and then take the negative of this vector. Sorry, the other one. So I take this vector and take the negative of this vector. So I do something like this. So I'm trying to draw this parallel to this one. So that would be negative of V1. And then basically the sum of those two, this is the change in the acceleration. Oh, sorry, change in the velocity. Okay, so that's basically the change in velocity vector. And then depending on how far, what the time difference is between V1 and V2, I would just divide by that. Now that is just a scalar, so essentially the direction of this would be already fixed. We already know it's pointing sort of this way, and then adjust the length of that vector basically by dividing by some time interval. Okay, so that's basically average acceleration. And then for instantaneous acceleration, it is again the limiting case of these two. So imagine you take V1 and V2 very, very close together. So V2 is going to be here, and in that case, quite different. Okay. So in that case, V2 is going to be much more similar to V1, right? So if it's just only a tiny bit along there, then it's going to be sort of like this. So this is another V2, but it's sort of just a smaller time interval. And but you can still see that there's going to be some difference between these vectors, and so the change in the velocity will be approximately something like that. And then you can see that this vector is somewhat pointing in the same direction as this acceleration, and this would eventually give you the instantaneous acceleration by taking the limiting behavior as you put this second vector close and close together to the first one, then this and then you divide by the time, then you basically approach some particular vector, which is the instantaneous acceleration. But again, in terms of computing this, it's actually in a way much simpler. You just take the derivative of whatever the formula that you are given of the velocity, and you just take the time derivative. So just look at the x component of the velocity, take the time derivative, that's your acceleration. Y component, that's your time derivative, is your y acceleration, and so forth. Yeah, okay. All right, okay, so let's try this question now. So here are 4 descriptions of the position in meters of a park. Oh, how do I get rid of this? Okay. 4 descriptions of the position of a puck as it moves in an XY plane. Okay, so X is some formula like that. Y is that. Okay, so we've got 4 different formulas like this. So this one we're given it in this vector notation. Here we're given it for each of the coordinates. Now, are the X and Y acceleration components constant? Is acceleration a vector constant? Okay, so, well, let's first look at this. So the X and Y acceleration components constant. All right, so why don't you have a go at that, and then you can put your answers in the chat. Yeah, sorry. So actually, I don't know why I have 2 sets of multiple choices here. So why don't we use the one on the right? Okay. Okay, so forget about these multiple choices on the left. Let's just use the one on the right. Right. Yes. Yeah. So a couple of you saying B, which is I would agree with that. And so maybe somebody can say, like, so what is the method to work out whether it's constant or not? How did you work out whether it is constant or not? Well, I think some of you must know because you got the answer right. So what did you, right, okay, yes. I mean, I just meant just the method. Actually, I would say that the method that I would use to work this out is, I see, okay, so maybe, so Tanya, I think maybe your logic is that because the formula for the position sort of follows the same kind of formula as for the motion with constant acceleration that we learned in the last chapter. Therefore, it's constant acceleration. Yeah. So yeah. Okay. So I didn't quite think of it like that, but that's maybe a way to think about it. Yeah. So that's correct. But maybe the more kind of general method that you can always use for questions like this is to just look at what the time derivative looks like. So for example, we're asked to find the accelerations here, right? And so acceleration is the time derivative velocity, but it's a second derivative of the position. Right? And basically for the vectors, the story is all the same. It's just that you just look at the X and the Y components separately. So for example, for this one, for part one, you basically look at the second derivative of this position. And so I hope this is sort of simple enough that you can more or less do it in your head. But so for example, here, the first derivative velocity in the x direction, so velocity x, would be minus 6t plus 4, right? And then the acceleration, you just take the derivative of that again. It's a second derivative, and this will be minus 6. So basically, it's a constant, and so that's why 1 is a example. Well, okay, sorry, we should do this one too. So Vy, so we have to check both of them are constant, right? So this one's going to be 12t, and then Ay is 12. Okay, so that's an example where it's going to be constant. And for 3, it's basically the same kind of thing. And basically the key point here, and the reason why you almost don't have to explicitly calculate it, is because you know how with the second derivative, you're going to take the second derivative of these formulas, and you know that basically something like t squared is going to, after the second derivative, it's going to be a constant, because after the first derivative, t squared goes to t, and then after another derivative, the t just goes to a constant. And so you almost don't really need to work out exactly what these numbers are. You just have to look at these formulas and go, oh yeah, this is going to disappear when you take the derivative. This is also going to disappear when you take the second derivative, because 4t goes to 4, goes to just 0. And then so basically all you're left with here. So you just kind of looking for what the form of this formula is, and basically it's just a polynomial, like it's a second power here. Now the situation is different here for number 2, because here the first derivative is going to be, okay, let me take the derivative of this, it's going to be minus 9t squared, and then this is going to be minus 4. Then second derivative, ax, take the derivative of this thing again, minus 18t. And that's not a constant because that is changing with time. So if you looked at the acceleration at time 0, it would be 0. If you look at the acceleration at time 1, it'd be minus 18 meters per second squared. So acceleration is changing, so it's basically not constant. And you can easily spot this because it's a third power here. So this one is going to be constant. This one's constant. This one's also constant. It's going to be actually 0 because there's no second power of t. This one is going to be not constant because it's got a cube. And if it here would be definitely constant because this is already constant in position. So basically, it's 1 and 3. And the quick way to do it is simply to look at the form of the formulas here. So, for example, say instead of these kind of powers of t, say you had some other formula like sine of t or something like that. In that case, do you think that could ever be constant? So, for example, say x was something like sine of t. So, in that case, would that be constant acceleration or not? Okay. Too hard? Okay, so let me try and give you an argument of why try and work out what it would be. So say x was sine t, right? Then in that case, Vx would be cosine of t. And then Ax would then be minus sine t. And well, this is certainly not a constant, because if you take it with at different points in time, the acceleration is going to be changing. So, for example, at time equals 0, this will be 0. Some other time it could be -1, or time of say pi/2 would be -1, so forth. So, in fact, if you had pretty much any kind of formula, so for example, if you had anything else like exponential t or some other formula, generally it's never going to be a constant, because usually formulas with some form like e of t or sine of t or something like this is going to, when you take the derivative, it's going to give you other particular formulas. And so these kind of powers like polynomials, and then particularly like the polynomial is say just a second power or something like that. This is just actually maybe the only cases where you take derivatives and it becomes a constant eventually. Okay, so hopefully that is clear. Just rub this stuff out. Okay, so now we can get onto projectile motion. So with projectile motion, it's basically an application of what we've learned so far, or again, a sort of a special case. And the most important thing that you need to kind of remember is, well, so firstly, in projectile motion, what is the situation we're looking at? So we're looking at some kind of problem that generally looks like this. We've got some object, we're on Earth or some planet, I suppose, usually Earth, and you are basically, projectile motion means you are kind of throwing the object or firing the object with some initial velocity, and it's in the air for some amount of time. And of course, if you throw anything, that it's going to fall to the ground eventually. So basically, it's an example of constant acceleration, as we learned kind of in the previous chapter, because as we did in chapter 2, was basically when you throw something in the air, you have force of gravity, which is always pointing exactly down, and that's always accelerating the object down. Now, this is basically almost the same as that, except that we've also got some movement in the x direction. So in the example that we looked at in chapter 2, basically we just looked at something that went straight up and then straight down. But in this case, we're going to look at something where it's going to sort of be fired and fly through the air and go down. And so basically we've got a mixture of movement in the x and the y direction. And like many physics problems, there's, when you first look at something, it looks kind of quite complicated, right? So this actually looks like a problem that is way more complicated than the example where it's just going straight up and straight down, because this looks like, it's going across, and you've got some more complicated movement. But there's sort of a very important sort of insight that you have, or somebody realized somewhere, probably Newton, I suppose, not sure who had exactly had this particular insight. It's not really named after anybody, but the very important piece of insight is that basically you can consider these two movements in the x and the y direction as being completely independent. So it's not that basically, you know, you have some more complicated movement where somehow this is fundamentally more complicated than the original up and down example. It's really just that it's really exactly the same. It's just that it so happens that there's also an x movement that's happening at the same time. So, or put in sort of maybe better phrasing than what I just said there, is that in projectile motion, the horizontal motion and the vertical motion are independent of each other. Basically, neither motion really affects each other. So we can really just look at this as kind of two sets of motion that are just happening to the same object at the same time, but equation-wise, they're just completely separate, right? It doesn't really, you solve for the x component and then you solve for the y component, and they just got to do with each other in terms of the maths, right? So in terms of the acceleration, we know it's straight down. So the acceleration is some vector. It's going to be pointing down. The x component is down, and the y component is going to be minus g in this case. Okay, so right. So maybe I should have had this slide open when I was explaining it, but let's just go through this again just to so you get the point. So the thing on the right here is the actual movement of the projectile. So we've got something which is launched with some velocity, it's pointing this way, and there's some angle here. And so we can work out what the x and the y components of the velocity is. Well, if we just follow the trajectory here, then you know we can sort of qualitatively figure out what is happening to the velocity vector. So as it's sort of climbing up here, we can see that the y component of the velocity is just being reduced a bit. Over here, we can see that the y component of velocity is in fact 0. So this is you know, at the top of the motion, and so it's no longer going up. In fact, it's turning around, and it's going to come back down. So the y velocity is actually just 0 at this point. Over here, the y velocity is now going down, and right at the end, it's of course heading down quite fast, right? And so the point is that, and in terms of the x component, from what we just said in the previous slide, basically the x component is totally independent of the y component. So all that stuff is happening to the y component, but for the x component, basically we can think of it as a separate problem. So the the x component of the velocity, in fact, is actually not changing throughout its whole motion. So the x component here is the same as the x component here, as it is here, as it is here, as it is here. So we can kind of separate these two into two different, two kinds of motion, which is happening to this object at the same time. So if we look at the x component here, it's just moving at constant velocity. So it's actually just like a particle, which is just, you know, moving at constant velocity, you know, from start to finish. So basically, you know, something, nothing very dramatic is happening to it. For the vertical one, this is just like we learned in chapter 2. Initially, it's going up, and then it's slowing down. So just look at the particle slowing down, coming back down. And basically, both of these two things are just so happens to be happening to the same object at the same time. Okay, so yeah, so to kind of prove to yourself, if you were to do an experiment where to sort of verify what I just said, then maybe this is the kind of experiment that you do. You would compare the motion of, say, two balls, one which is just going straight down, and one which is going across, but also down. And then this is a stroboscopic image. So basically that means that you got your camera shutter open, flashing lights at it at some equal time interval. And so you can see where the positions of the balls are at each of these times. So this is the first flash, second flash, third flash, fourth flash, fifth flash, and so forth. And the key point that you notice here is that the vertical position of the balls are exactly aligned at each point in time. So this is another point in time. This.
你要吃啥呢？我叫外卖。如果你跟我一起吃吗？
Okay. All right. So. Okay. So maybe can you turn your mic off?
你可以再试一下，没有关系。9点了。嗯。我上9点。你家有一点9点。哦操
！Let's see.
7点半起来了。
Where is this coming from? Okay. All right. So. Quite work out who's talking there, but anyway, so at each point in time you have these balls and they're exactly the same vertical position. So over here it's the same vertical position, over here it's all the same vertical position. Okay, so that basically shows you that it doesn't really matter that this yellow ball is moving to the right. The fact that it's got this x velocity is completely irrelevant actually to the y movement. So this is basically how you sort of experimentally verify that this is these are sort of independent movements. Okay. Right. So there's a kind of an interesting consequence of this, which it's sort of somehow a little bit kind of it's hard to get your sort of head around. But I mean, when you write down the equations, it's kind of clear that it's true. And so this is sort of the setup that we're going to look at. We have basically some kind of projectile, so something coming from a gun. I'm going to shoot this can, and the point is that the moment that you shoot this gun, this releases this can from some position and it starts to fall. Now the bullet from the gun is obviously, well, usually the motion of the bullet is so fast that you don't really think that the bullet is going to sort of fall under influence of gravity because it's just going so fast. But suppose this is not a very strong, it's not a very powerful gun, so that it doesn't shoot the bullet extremely fast. Now in this case, what you can kind of show is that so long that this can is released exactly the same point that this gun is releasing its bullet, it actually doesn't matter how fast you shoot the bullet, or even it doesn't matter anything about like how much this can falls. This bullet will always hit the can. Okay, so just to convince you that this is true, so let me show you a video. Basically does this demo. Yeah, so maybe I'll turn down the sound. Okay, so we're basically got this kind of physical setup. So instead of a can, we've got a toy monkey here, and this is a gun that is shooting golf balls. The monkey. And it's hooked up so that it releases the monkey exactly the same point that the gun is going to release the golf ball. Okay. All right. Okay. So that is demonstration of the effect. Let's go back. Okay. All right. So basically, we have to work out, why does this always work? Why it seems sort of kind of magical, because you know, clearly you don't really need to even shoot the bullet very fast at all, right? Like the gun is actually quite the golf ball is going kind of pretty slow. The monkey was falling, actually quite a lot, and regardless of basically all that time interval, and the fact that both objects are kind of falling, it hits it perfectly. So so why does this work? So if we do the analysis, it goes something like this. So first, consider the case when there's no gravity acting on this, right? So when you do this experiment, first what you have to do is you have to line up your gun so that it will, if there was no gravity, then it would hit the can perfectly, right? So you've lined up your gun so that at least the initial motion, if there was no gravity, it would hit the can. So there's some kind of angle that you need to shoot it at, and that makes sense, because obviously you need to get some kind of angle, right? Obviously, if the gun's pointing in the opposite direction, it's never going to hit it, right? So at least there is that initial direction that you need to get right. So if we look at the position of the bullet, and let's consider the case without gravity first, then so there's some time interval where this thing is flying, so let's call that t, and this y0 is the okay, sorry, let me get my definition straight. Okay, right. So y0 is in fact the position of this, where the initial point of the can is, right? And so after some time t, this bullet will travel here, and the position of this will be v0 t, where v0 is like the y component of the velocity. So what we do here is, so there's some time interval where the bullet is traveling through the air and hitting this can, and so this is the basically the position of the bullet after it gets to this can. And this is the coordinates of the monkey, and in this case the can. And because the initial position of the can is actually exactly where the position y is, so this one is defined always at position 0. Okay, now if you include gravity into this equation, so for the bullet, basically if you look at the y coordinate of this, we know from the 5 equations that we did, I think it was like the second equation, that the position of the bullet is going to be affected by gravity, and because gravity is down, this will be adjusted by a factor of -12 gt squared. So this bullet will go down by a distance half gt squared, which is the basically the time is again the time that it's flying in the air, and g is the acceleration due to gravity. Now for the monkey, the distance that it actually falls is also half gt squared, and so the key point is that the time that the can actually falls is actually exactly the same as the time that the bullet is in the air. And so because the monkey also falls by the same distance of half gt squared, so this height here that it falls is exactly basically the same for the bullet or the monkey. So basically, sort of just to give you a rough explanation, the amount that anything falls is always the same, regardless of basically it's got some kind of x component to the velocity or not, or even in terms of the initial velocity, if you have it so that it is going to hit the can with 0 gravity, now the additional amount that it falls because of the fall under gravity, basically that amount will be exactly the same, and then so you can basically always hit the can. Okay, so hopefully that it's reasonably clear. So okay, so let's try this question. At a certain instant, a fly ball has a velocity of 25I minus 4.9 j. So has the ball passed its highest point? And so we're talking fly ball, so this is the context of baseball. So basically what we're talking about is, the batter hits the ball, it's flying through the air. So this is going to be some projectile motion. Here's the velocity at some point in time. And it's asking whether it is past the highest point or not. Yes, so when it's saying yes, so yes, I think that is correct. So basically the first thing to see is, is this ball traveling up or down? And we can see from the y component here, which is the vertical motion, that it's negative, so it's already on its way down. And well, in fact, I think you almost don't really need to use too much physics here. If it's traveling down, then I think you can appreciate that it's already past its highest point because, you know, we're talking in terms of baseball, it goes up and then it comes back down. So anywhere along first part of its trajectory, it should be actually traveling up. So if it's traveling down, it's already past its highest point. Okay. So in terms of equations, how do you work this out? Then basically we use the kind of equations that we already derived. And so we've got in our armory these 5 equations, and this is the equations that we use for constant acceleration. And for the horizontal component, actually, usually you almost don't really need to use these equations because basically everything is pretty straightforward. So if the horizontal acceleration is 0, in this case, well, a lot of these equations simplify. So for example, if you have acceleration 0 for the first equation, then it just says that the velocity at any point in time is the same as the initial velocity because the second term doesn't exist. Acceleration is 0, then this just says that the displacement is equal to the initial velocity times time. So again, that's just basically your sort of distance equals speed times time type formula. This one, if this second term is not there, then again, it just sort of says velocity is the same as the initial velocity. The velocity doesn't change, so it's basically equation 1 squared. This one doesn't have acceleration anyway. And in this case, as we know from equation 1, V0 is the same as V. So again, this just reduces to something like displacement is equal to velocity times time, because there's a half here. It's be 2V0, and then we just V0 T. And here again, it'll be, yeah, position is velocity times time. So you almost don't really need to use equations for the horizontal part, because it's just the only real equation there is that position is speed times time, which you probably know already. So yeah, so in this case, if you're given the initial velocity and the angle, then the horizontal component of the velocity is V0 cosine theta. And then from that, you can work out position just by multiplying by time. Okay, so that's the horizontal part. Now for the vertical part, so this is exactly where you can just apply the usual, these 5 equations. And in this case, the acceleration is the acceleration due to gravity. So taking the vertical velocity to be V0 sine theta. So that's the initial velocity in this case. And the gravity is minus g. So in this case, that's the vertical velocity that you use. Or in this case, we can also use this third formula. In this case, we're talking about the y component of the velocity. The initial velocity is a sine factor here. And we're talking about the y displacement. So that's that. For equation 2, we've got the vertical position. Yeah, so basically the only difference here is that the initial velocity is sine theta. Okay. So just to kind of visualize what all these formulas are talking about, I just plotted some of these velocities. So for example, if you look at the y component of the velocity with time, so just this one, basically what you see is that the velocity, the y, if say the initial velocity was right, so my initial velocity is 10 meters per second, and theta is 45 degrees. So it's projectile motion where it's going to be launched at 45 degrees like that. Now the initial velocity is this will be something like 7 because cosine of 45 is 1 over root 2, which is about 0.7. So 0.7 times 10 is about 7. And then as you evolve it in time, basically it's initially sort of going up, but it will start to turn around and go down. This is the point where it turns around. This is the peak of its motion, and it's going to go down from there. This is the position equation. So with respect to time, this is the height. This is actually time. So it kind of almost looks like the projectile motion itself, but it's not. This is the time. This is the y position, and this is the time that it's taken since launch. So at some point here, it will be at the same level as the initial position. So if we're on level ground, then this is the point where it hits the ground again. So you launch it, and it might hit the ground. I've extended it here because in some types of situations, it can actually start to go further down. So for example, if you launch something off a cliff, then it has the opportunity to go further down than where it started from. So if you're launching off a cliff, it could go further down than where you launched it from. For the other equation, which connects the position and the velocity, so this is the vertical position. So this is how high you are. So it's maybe a bit confusing, but it's how high you are is along the x-axis. And this is a quadratic equation, so there's always two solutions. So when you do the square root, there would be a plus and minus factor. And so there are two positions for each position. So for example, here, y equals 0 means that's the height that you started at. Right? And there's two possible velocities because it's just like here. When you start, there's some velocity in the y direction, which is physically going diagonally, but just in terms of the y direction, there's some positive movement to the object. So it's initially going up, but then it will, when the position is 0 again, there's another point here, which is around about 1.5. And so we can look at this graph, and we can see that the velocity is actually negative here. So the initial velocity was positive here, but it's negative over here. So that's why there's actually two velocities here. Over here at 2.5, we can try and read off where 2.5 is. Actually, that's the apex of the movement. At this point, the velocity is actually 0. And so there's no plus minus because it's exactly 0. Okay. Right, so these ones, I think maybe it's better if we just leave this for next lecture because I just want to go through and maybe just derive some of these formulas on the board for you. So I think we'll do that when we've got a proper whiteboard. So I think we'll finish up there. And as for the homework, I think there was an announcement by the recitation instructor that for those of you who are in Shanghai, please just hand in your homework in the Thursday lecture. but remote students, you can just send it by email as well. Okay, so any questions on today's lecture? Okay, if not, then we'll finish up there and I will see you on Thursday. Bye.
Bye, thank you.
Yeah.
Thank you, Professor.